Swayam Prabha. Digital India. Educated India.
Hello everyone, today I am going to deliver a lecture on plasma arc welding, which is a fusion welding process. In short form it is called as PAW. P represent plasma, A represent arc and W represent welding. These are the contents of today's presentation. That means here I will cover introduction first, then setup of this plasma arc welding process, then what are the equipment of this process, then what is the power supply generally used in this process, then principle of this operation, then current and its operating modes. I will also discuss about current and gas flow decay control, then plasma and shielding gas, and finally I will discuss about advantages, disadvantages and its applications. Generally, depending upon the liquid state and solid state, what happens, this welding techniques or you can say joining technique can be broadly categorized into three different categories. One is called liquid state welding. So, in this category generally you can see all the fusion welding techniques comes. These things you should keep it in mind. Fusion welding techniques, what do you mean by fusion welding technique? That is very well known to you. Fusion welding techniques means where the temperature goes of the parent material or the base material beyond its melting point temperature. These things you should keep it in mind. That means in this case the material become in liquid state. That is why these types of welding techniques is called liquid state welding techniques. Another one is called solid state welding techniques. Here the temperature generally does not cross its melting point temperature. Here the temperature lies below its melting point temperature, and here the parent material or the material which we are going to join, that material generally is in solid state. Like here the material become paste type and finally we join the material. Okay, so here the material does not cross its melting point temperature. But another types of welding process which is the combination of both solid and liquid state welding. So, solid and liquid state welding, here one part of that welding techniques generally that is in liquid state, another part of the is in solid state, that you can say. That means which part is in solid state and which part is in liquid state, that we should know. Here one thing you should know, that means here the liquid state part is filler wire, that generally whatever the filler wire we use to fill the gap and for joining purpose, that filler wire goes beyond its melting point temperature, whereas the parent material or the workpiece which we are going to join, that part temperature does not cross its melting point temperature, that means that is in solid state. So, here as in this welding process two different phases are present, that is why these types of welding techniques is called solid liquid state welding techniques. In these categories generally the soldering and brazing techniques come. In this course I will give lectures on different important types of conventional fusion welding processes which are widely used in manufacturing industries. I will also cover different types of solid state welding process. One of the solid state welding process nowadays is very popular welding technique, that is called friction stir welding process. In details I will cover about that techniques. I will also cover different types of solid liquid state welding techniques. Today I will start our course by delivering a lecture on a very important fusion welding process, that is called plasma arc welding process. In short, it is called PAW. So, you see this plasma arc welding process which I am showing in the right side of this figure, you can see it generally can be defined as a gas shielding arc welding process. It is a gas shielding arc welding process where generally the collisions of metal is achieved due to the heat transfer by an arc that is created between a tungsten electrode and workpiece. From this figure you can see here generally this arc is generated between a tungsten electrode. So, here you see this inner one is called tungsten electrode, it is a non-consumable electrode. So, during arc generation it is not melted, or you can say it is not consumed in welding process. Okay. Now, this is the arc, you see here I have written here plasma arc, or you can say plasma column, this I am representing here. This arc generally generated between this non-consumable tungsten electrode and this workpiece you can see from here itself. This arc generally constricted by a copper alloy nozzle orifice. You see here I have written already, this is a water cooled copper nozzle, here I have written. So, you see this is a water cooled copper nozzle, through this arc is transferred from electrode to workpiece. Once it transfer from electrode to workpiece, at that time this arc is constricted means instead of spreading out its diameter reduced, what I am telling, understand. That is why due to this constriction, as this diameter reduced significantly, that is why what happens here, very high intensity of heat we can get. Intensity of heat in the sense like heat per unit cross sectional area will be high, because same heat we are applying in a lesser cross sectional area. Instead of spreading it out, here we are constricting the thing. That is why here generally very high intensity heat we can get, okay, due to this constriction of arc, because here the arc is reduced its diameter due to this water cooled copper nozzle. This you should keep it in mind. So, outside of this water cooled copper nozzle, there is some another orifice or another nozzle we can say. Through this nozzle generally you see this black arrow I have provided. This black arrow represents the shielding gas. Outside of this copper nozzle there is another nozzle, or you can say orifice is there, through which there is coming out this shielding gas. Shielding gas, what is the purpose of this shielding gas? It is very well known to you. It is generally used to shield the whirlpool as well as this arc from atmospheric contamination, because once it is protecting from the atmospheric condition, then what happens, there will be less chance of oxidation, because we can prevent the oxidation, which is a very important requirement for arc welding process. Now, here this plasma, or you can say this arc plasma which is generated here, it is formed by the plasma gas. You see this plasma gas generally passing through inside the, you can say inside the copper nozzle you can see. So, this plasma gas once it come into contact with this arc, at that time this some of the portion of this plasma gas ionized. What I am telling, understand. Once it is ionized, then this plasma gas converted to plasma arc. What I am telling, understand. That is why what happens, so plasma is a combination of ionized gas, you can say. There can be some non-ionized gas molecule, and there can be some that means ion and electrons. Okay. That what I have written. So, plasma is a gaseous mixture of positive ion, negative electron and neutral molecules. Whatever the plasma here you have seen, that is generally a combination of a gaseous mixture. Here you should keep it in mind, as this arc is constricted in between this water cooled nozzle, that is why here the temperature rise comparatively very high than the conventional arc welding process. Here that is why I have written, in this welding process we can get a typical value of temperature which is the order of around 50,000 degree Fahrenheit, whereas in conventional types of arc welding process it is within a range of 10,000 degree Fahrenheit. Okay. These things you should keep it in mind. Now, here I am just showing the detailed setup of this plasma arc welding process. Why this is called plasma arc welding process? Because here is a simple arc is also there. It is called plasma arc welding process because to generate the plasma, Here we are using a separate plasma gas. Here you can see, there generally we use two gas, one is called plasma gas and another one is called shielding gas. But in other welding process like TIG welding process, there you can see there is only one gas generally used, which is generally used to shield the arc or whirlpool. But here one gas we are using to develop this plasma and another gas we are using to shield the arc or whirlpool from atmospheric condition. Now here the detailed setup here I am showing. Here generally this power source is there. Okay, this power source is one terminal is connected to the electrode, that is non-consumable electrode, you can see here this is non-consumable electrode. Another terminal is connected to the workpiece. Now you are very well familiar where we should use negative terminal and where we should use positive terminal. In case of non-consumable types of electrode, generally it is preferred to use direct current electrode negative polarity. What I am telling, understand? Electrode negative polarity once we will use, once the electrode will be negative polarity, then the electron will come out from this negative polarity and it's moved towards the workpiece. Because if it is negative polarity, then chances of generation of heat in electrode will be less. That means in case of DCEN, you can say DCEN polarity, you can write in electrode, that means tungsten electrode, here heat generation percentage is around 30% and in workpiece generally it is 70% around. Okay. So, here in case of DCEN, when its electrode is negatively connected, then less heat is generated in tungsten, which is desirable, because here we do not want to melt the electrode, because if higher heat will be generated in electrode, there is a chance of melting that electrode, and what happens, it can make contamination with this weld material and it can make some defect, that which we want to avoid. Okay. Now, that is why DCEN generally here I have shown, that means here direct current power supply we are negative terminal we are connected to non-consumable electrode, that is tungsten electrode, that you can see here. Now, another terminal, positive terminal is used in workpiece. Okay. Now, here outside this tungsten electrode generally put inside the copper nozzle as well as shielding gas nozzle. You can see this green color arrow represent the plasma gas and this blue colored arrow represent the shielding gas. Okay. So, here you can see that two passages of nozzle are there, two passages, one passage is used for flowing of plasma gas, another passage is used for flowing of shielding gas, you can see from here. Okay. That is why this outside I have labeled here by writing shielding gas nozzle, and inside one I have written as constricting water cool nozzle. Okay. Now, and this is the setup of you can say plasma arc welding process. Here one thing you can observe that here there is some other connection is there, that is called resistor is connected with this copper nozzle boundary, or you can say with this copper nozzle, water cool copper nozzle. Why this is required? Because this is required because when we start the arc, at that time generally this arc is started in between this electrode and this copper nozzle, in between this electrode and this copper nozzle. To generate the arc initially, this circuit generally used, this resistor circuit, that means which is connected to the water cool copper nozzle and electrode. So, once this two terminal, positive negative terminal is connected with this electrode and what it is called copper cool nozzle, at that time generally the arc will be generated in between. Here I have shown, here you can see this arc will be generated between this copper cool nozzle and electrode. This is called non-transferred arc. Okay. This you just keep it in mind, later on I will discuss in more detail. Okay. So, this is the equipment of plasma arc welding process. Here I have shown here everything in details. This is the basic plasma arc welding system, you can say. It generally consists a power source. This is generally power source. In case of plasma arc welding process, generally direct current power source is used. That is why here I am writing power source, direct current power source is used. So, here you see there is a water cooler, here you see here is a water cooler, this is generally water cooler, this I am writing here. This is a water cooler, from here generally coolant out and in taken, but there is a circulation of coolant is there, because what happens, we have to cool this torch, because I have already shown you previously there is a water cool copper nozzle is there. What I am telling, understand, that means whatever the copper nozzle is there, inside that nozzle there is a cooling system, that means there is a channel through which this water is flowing, so that this copper nozzle should be cooled. Okay. So, that is why here you see this water cooler, which is generally used to supply the coolant in this torch. This is the torch, here I am writing this is the torch. Okay. This torch, inside this torch there are two nozzles simultaneously, one is copper cooled nozzle, another one is outside nozzle, which is used to supply the what is called shielding gas, correct. There is two different types of gas supply is there. One is this is generally called plasma gas, and this is called shielding gas. What is the type of plasma gas, what is the type of shielding gas, everything in details I will discuss in subsequent slides. Generally for plasma gas always preferable to use argon gas. Why? That things also I will discuss. Now you see this power source operated remotely, that is why here I have written remote current control. We can control this power source remotely also. Okay. Now there is a switch which is generally used to start and off this machine, that is also I am showing here. Now you can see this power source, plasma gas, shielding gas, water cooler, everything is connected with a particular location. That location is called plasma control console. Okay, it is called plasma control console. You can see here, okay, this is called plasma control console. So, this plasma control console generally control the entire operation, you can see. By this generally entire operation is controlled. So, this everything is connected at this plasma control console. From here you can see there is a plasma gas hose means plasma gas pipe, through which generally this plasma gas is supplied to the torch. Another one is you see called shielding gas hose or shielding gas pipe, through which generally shielding gas is passed through this pipe and it go to the torch. And here you see in between generally there is a two cable, this is one cable, this is another cable. One is negative lead, this is called negative lead, and this is called positive lead, you see positive lead. And there is another pipeline are there, one is used for coolant in, another one is used for coolant out, which I have written here. This is coolant in and coolant out. So, you see these are the entire equipment, or you can say entire setup of a plasma arc welding process. So, here you see this is the nozzle, in this nozzle here the arc is started between this workpiece and you see torch, this is the arc, you can say this is the arc. Okay. Now, here what types of power supply generally used, that also you should know. Here what I have told you, as it is a non-consumable types of welding techniques, where generally the electrode is not consumed here. That is why it is better to operate in a continuous and steady mode, where DCEN is preferable. DCEN, what is DCEN? Direct current electrode negative is preferable, because we want less heat to be generated in electrode. That means otherwise what happens, there is a chance of overheating this electrode and melting that electrode, tungsten electrode, which can make some inclusion in the weld. That is why we should use DCEN. But here one thing you should keep it in mind, this DCEN also you can use in two way, one is steady state or continuous way, another one is called DCEN's pulse current mode. Pulse current mode means here there will be a direct current, but which will be in pulse mode. Pulse mode in the sense there will be a peak and there will be a down. What I am telling, understand? There will be, you see let this is positive, this is negative direction. So, it is a pulse types of current. Pulse means there is a peak pulse, this one is called peak pulse, and this one is called background pulse. What it is called? Background pulse, background pulse. Okay. This is called peak pulse, peak pulse. This is generally represent current and this axis represent time. That means, with time this current magnitude varied, but current magnitude always is in same state. What I am telling under same state means it is in positive, means direct current, there is no zero crossing, you can see there is no zero crossing. Okay. So, that is called DCEN pulse current. Here the current is in pulse form, and sometimes in this power supply also it is observed that there can be use what it is called, there can be use variable polarity mode. Variable polarity mode, what does it means? Variable polarity means there can be use both DCEN as well as DCEP connection with this electrode. What I am telling, understand? In this there can be this types of thing, that means this with time this current, with time this current can vary from positive to negative. So, in this case this is called variable polarity, where once you will variable polarity in one cycle and the more heat will be generated in electrode, and another cycle the less heat will be generated. So, there will not be continuous heating of this electrode. So, there will be less chance of melting of this electrode. What I am telling understand. So, sometimes this variable polarity also used in case of plasma arc welding process. Now, here one thing you should keep it in mind, this pulse current mode, that means this pulse current mode, it is a DC power supply, pulse current mode, it is a DC power supply, is often used when the application of this equipment for high current range. High current range where generally the keyhole is formed. What is keyhole? That also I will explain in subsequent slide. So, for keyhole mode types of application, generally pulse current mode is preferable. Pulse current DCEN polarity is preferable, that means it is a direct current electrode negative always, but it is in pulse mode. There is a instead of continuous constant supply of what it is called current, here it is used pulse way. Then what happens? There is a peak and down. So, there is a less chance of means continuous heating of this electrode is there. So, in case of keyhole mode generally where the high current is used, there is a chance of a high heat. So, if there is a continuous direct current will be there, then due to this high current there is a high chance of what it is called melting of that electrode is there, though it is 30%, but due to high current more heat can be generated, correct. That is why it is better to use their pulse DC current, what I am telling DCEN current. Okay. So, if you use pulse DCEN current, then there is a less chance of continuous heating of that electrode at high heat. So, there is a less chance of this melting of that electrode, and there is a less chance of defective weld due to this melting of electrode. Especially once the current range above 100 ampere, they are generally preferable to use DCEN's pulse mode types of power supply. This you should keep it in mind. Okay. Now, we will discuss about principle of this operation. Once the equipment is set up and the welding is initiated, then the plasma and shielding gas are switched on. So, before starting of the equipment, generally this plasma and shielding gas is not started. These things you should keep it in. After equipment is set up and welding is initiated, then you have to start this plasma and shielding gas. Okay. Once we start this plasma and shielding gas, initially a pilot arc is struck between a tungsten alloy electrode and the copper alloy nozzle. This what I want to tell you. What is pilot arc? Because I have already told you, pilot arc means this is your electrode. So, outside of this electrode you can see there is one nozzle, and outside of this outside of this inner nozzle there is another nozzle. So, two set of gas generally here we use. So, initially a pilot arc is stuck. Pilot arc means this is your electrode. So, this electrode once we start the equipment, initially a pilot arc is started. That means, in our setup I have shown there is a connection with resistor with this copper, this is generally copper nozzle, this is copper nozzle, or you can say copper orifice also, it is sometimes called copper cool nozzle. So, a arc which is struck between this electrode and this copper nozzle, this arc is called pilot arc, pilot arc. So, this arc initially started in between this copper arc and electrode. Okay. This is a non-transferred arc, because this arc is not transferred to the workpiece. Here you see this arc is not transferred, this is called non-transfer arc mode. So, you just keep it in mind. After that, once we start the actual welding current, then the arc transferred, then this arc transfer from this electrode to workpiece. That means, this pilot arc then transfer from electrode to arc, that what I have written here. After that, when the selected welding arc is initiated, then the arc is transferred from electrode to workpiece, which I have written directly. Okay, here you can see. So, you see at that time generally this weld pool is formed here, this weld pool is formed here, and welding is done. What I am telling, understand, these things you should keep it in mind. So, before starting the actual arc, there is a arc which is called pilot arc, which is generated in between this copper nozzle and this electrode, which is generated by a system which I have already shown you in setup. Here also that system, there I have represented that system by a resistor. Actually, there is used generally high frequency open circuit voltage. By this very high frequency open circuit voltage, a pilot arc is generated. This pilot arc generally low intensity arc, you can say. So, after that, once we set the actual welding current, at that time generally this arc is transferred from electrode to workpiece. At that time, weld metal is formed here and welding is done here. Okay. Now, in case of plasma arc welding process, we can see two distinct operating mode. What I am telling, understand, there is two distinct operating modes. One is called melt-in mode, or this is sometimes called conduction mode. Another one is called keyhole mode. These two mode details I will explain in a subsequent slide in detail. This is a very important part of this welding process. Melt-in mode means, here in this melt-in mode you see this first figure represent the melt-in mode. Here a bowl shaped, you see a bowl shaped portion of the workpiece material melted under the arc. Here you see this is a bowl shaped molten material which is generally melted below this arc. You see this is the arc, below this arc the portion of base material melted here, you can see workpiece material melted here. Here this heating of the material is done by conducting heat from this arc to workpiece by conduction way, that things I have written here. Here the heating of the workpiece occur by conduction of heat from the plasma contact with workpiece surface inward. So, whatever the conduction of heat is occur, here generally this conduction of heating is occur from this arc to workpiece by conducting heat to inward direction. Now, these types of melt-in mode or conduction mode types of welding process used for very low thickness types of material, especially the material thickness which is varying from very low thickness like 0.025 millimeter thickness to around 3 millimeter thickness. Till this 3 millimeter thickness plate generally it is preferable to use what is called conduction mode types of welding, because here penetration is comparatively less, you can say. That means material, that is why it is just a portion of material below the arc melted, okay, and after that on this arc move away, then it solidify and welding is done here. Now, right side of this figure I have shown the keyhole mode. Here you see there is a full penetration, you see there is a full penetration of this workpiece is there. So, here is a keyhole is made in between this arc, you see in between this arc and the workpiece thickness direction. Here there is a hollow keyhole is developed. What I am telling you, there is a hollow keyhole is developed. Everything in details I will discuss in subsequent slide. So, here is second mode is called keyhole mode. In this mode the arc fully penetrate the workpiece, what I have told you, what I have told you, that means this is the workpiece, whatever the arc is, this is the electrode, in between the electrode the constrict arc when it is come. So, here generally there is developed a through thickness hole, you see there is developed a through thickness penetration, there is a through thickness penetration, that means this arc is fully penetrate and what happened, it come out like this. So, some portion of arc you can see which is coming out below this workpiece, that is called efflux. What it is called? Efflux, E-F-F-L-U-X, okay, efflux of this arc. Okay. So, here you see in this mode this arc is fully penetrate this workpiece, generally fully penetrate and forming a constrict keyhole through the thickness. Here there is a, you can see there is a constrict keyhole, there is a constrict keyhole, here you see there is a constrict keyhole is formed throughout the thickness of the workpiece. Here the molten weld pool or this molten metal flow around the arc is drawn by surface tension or capillary force to fill the gap. So, once these torches start moving along the welding direction, at that time generally this keyhole is filled by molten weld material, which generally comes in this gap by capillary flow. You know this, what is the capillary flow. So, I am not going in details. So, once this arc move along the keyhole line, then what happens, surrounding this keyhole, you see surrounding this keyhole there is a molten material, correct, there is a molten material. This molten material, how this molten material is sustained, you see here I am just little bit more detail I am showing. Here this is the keyhole, this is the keyhole. Now, through this keyhole there is a constrict arc, you see this is the constrict arc. Okay. Now, you see this keyhole is a vaporized molten material gas, this keyhole is formed due to vaporized molten material gases. So, this molten material gas has a vaporized pressure, that this molten material gas or vaporized gas has a pressure, that pressure generally pull back the molten material from this keyhole region. What I am telling, understand. So, once the arc is there, due to this vapor pressure of this arc of this molten material, this keyhole is remain as it is during the keyhole mode. Okay. So, once this arc move from this region, then surrounding this keyhole there is a molten weld pool, that means surrounding of this keyhole there is molten material. So, these are all molten material, you can say molten material, molten material. So, once this arc go in front direction or along the welding direction, then this molten material generally fill this gap, this molten material fill this gap. How it fill this gap? This fill this gap by a action which is called capillary action. So, once it fill this gap, generally at that time, as there is no arc, because arc is already moving away from this region, there start cooling and it solidified and welding is done. So, it is, you can compare these things, that what I have written, with a hot wire through wax. That means, if a hot wire move through a wax, at that times you can see hot wire move away from this wax, behind this wire this wax start joining. Similar things happen here also. What I am telling, and this is a very important phenomena in case of plasma arc welding process. Okay. This keyhole mode generally use very high power density arc. High power density arc means this, whatever the arc is there, let this is the arc, whatever the arc here it is forming, this arc have a intensity, that this is the arc area, let this is the arc area, this arc area has a intensity which is around 10 to the power 9 to 10 to the power 10 watt per meter square. How it is coming? Let this arc has a power W. So, this arc power, once we divided this thing by using this arc spot area, this arc spot area A, let this arc spot area A, then what happens? This is actually watt per area. So, watt per area means watt per millimeter, which range is around 10 to the power 9 to 10 to the power 10 watt per meter square. It is a very high current plasma. This you should keep it in mind. Due to this very high intensity, it generally penetrates this workpiece throughout the thickness. By this keyhole mode, we can join around more than 20 millimeter thickness of plate also. That what I have written here. Penetration is very high. It's approximately 20 millimeter we can achieve. Now here another things you should keep it in mind, since the vapor cavity tends to trap the energy, actually what happens, as that is a hole, this trapping energy reflect around this hole, and due to these things this energy trapped inside this keyhole mode also, inside this keyhole. Depending upon this current and operating mode, the plasma arc welding process can be categorized into three different current mode. One is called microplasma mode of plasma arc welding process, another one is called medium current plasma, or this is also a melt-in mode types of plasma arc welding process, and third one is called keyhole plasma mode, which is developed here, which is keyhole mode. So microplasma and medium current plasma both have a melt-in mode types of phenomena, but in case of keyhole plasma, there you can observe a keyhole mode. So it's generally depends, once we vary the current, then depending upon the current variation, generally these types of categories of plasma arc welding techniques are there. So for these different types of plasma arc welding machine also available, like for microplasma arc welding machine, which is generally operated within a range of current which is varying from 0.1 to 15 ampere current, whereas in medium current plasma mode, here the current range varying from 15 to 100 ampere, and there is use keyhole mode where the current range is above 100 ampere. But here one thing you should keep it in mind, there can be overlapping of this keyhole and melt-in mode. Like what happens, it is observed that if you use a lower thickness of material, like for 2 millimeter thickness of material, we can get through thickness penetration by using 70 ampere current. That is why depending on the thickness of the plate, what happens, there can be overlapping of this mode. That means by medium current mode itself also we can get keyhole mode if you use lower thickness of material. That things exception also I have written. For example, keyhole mode can be achieved at 70 ampere at a 2 millimeter thick sheet. Generally this microplasma and medium plasma welding techniques is used within a range of plate thickness of maximum 3 millimeter thickness. Once it is above 3 millimeter thickness, there generally it is preferable to use keyhole mode. Keyhole mode technique generally have a very high power density. Due to this high power density, by using keyhole mode we can get high speed of the welding process also, what I have written. That means there we can use greater thickness of plate and higher welding speed also we can use over there. Now you see, depending upon this transfer of the arc from electrode to workpiece or electrode to this copper nozzle, this welding process further categorized into two different categories. One is called transfer arc process, another one is called non-transfer arc process. Transfer arc process, how it is look like, just here I am showing. Here you can see this is called gas tungsten arc welding process. In gas tungsten arc welding process also there is used a non-consumable electrode, correct? There is used a non-consumable electrode, and this non-consumable electrode and a shielding gas. You see only one nozzle is there. So through this generally this shielding gas is coming out, that you can see, and this is the arc, this is the arc, okay, this is the arc. So this is called generally tungsten or TIG welding process. So here only one shielding gas is used, but in case of plasma arc there can be, one is transfer mode, another one is called non-transfer mode. In transfer mode you see this power source is connected, one terminal is connected with arc piece, another terminal is connected with electrode. Whereas in non-transfer mode, one terminal of this power, so this is the power source, one terminal is connected to the electrode, another terminal is connected to the copper nozzle. What I am telling, understand? That you can see here. So this is called non-transfer mode. So once this terminal, in case of non-transfer mode, it is connected with this electrode and this copper nozzle, here whatever the arc will be developed, that arc generally constricted in between this copper nozzle and electrode, correct? Whereas in case of this transfer mode, here the arc is created in between this electrode and workpiece. So once this arc created in between electrode and workpiece and it is passed through this copper nozzle, then this arc generally constricted. That means arc diameter reduce, and it generally make the arc uniform diameter, and what happens, here the power density is increased, because as the arc constrict, same power is applying in lesser cross sectional area. That means spot size reduce. So, what we know, same power, if this same power, let this power is W, here generally this arc spot size A. So, if this A is reduced, that means once the arc constrict, then this A decrease. So, A decrease means this arc intensity means arc power per millimeter square. This, that means as area is decreasing, so this intensity is increasing. What I am telling, understand? So, in case of non-transfer mode, what you observe here, you see in the non-transfer mode generally arc is generated between this copper nozzle and workpiece, and transfer mode it is generally created in between what it is called electrode and workpiece. Okay. So, this transfer mode generally used for different purpose. This transfer mode arc generally used for welding as well as cutting purpose. So, here generally cutting or welding of ceramic, steels, aluminum alloy, copper alloy, titanium alloy, nickel alloy, different material, in different material we can use this transfer mode plasma arc welding process. Whereas this non-transfer mode welding process, here you see here as this power source is not connected with this workpiece, you can see there is no connection of this power source with this workpiece. So, you can transfer this nozzle from one workpiece to another workpiece without stopping the arc. There can be continuous movement from one workpiece to another workpiece. But in case of transfer mode of plasma arc welding process, in this case generally you can transfer continuously from one workpiece to another workpiece without stopping the arc, correct? That things also you should keep it in mind. That things only here I have written. So, in non-transfer process, this process generally utilizing the heat which is constricted in between tungsten non-consumable electrode and water cool constricting nozzle. Okay. This process generally produces plasma of relatively low energy density. Definitely it is low energy density, and this workpiece, here one thing you should keep it in mind, which I have already told you, the workpiece in this welding is not a part of electric circuit. So, we can transfer this nozzle from one workpiece to another workpiece without extinguishing the arc, which I have written. This non-transfer mode plasma arc welding process is used for welding, especially low thickness types of welding and welding material, and for a plasma spraying purpose, spraying, or you can say plasma coating purpose, generally this non-transfer mode plasma arc welding process used. Now, we will discuss what are the different types of plasma and shielding gases, and what is its advantage and disadvantage, that also we should know, and how we should use this plasma and shielding gases. Little bit more idea we will discuss here. Like here you see plasma gas is used for generating the arc, and shielding gas is used for protecting the arc as well as the weld pool from the atmospheric condition. What I am telling others, or you can say from the atmospheric contamination to prevent the oxidation. Now, here one thing you should keep it in mind, here plasma gas generally always used as a argon gas. Flow rate of this plasma gas is a very important thing, that I will show you in next slide, because always keep this thing in mind, higher the range of current, higher should be the flow rate. These things you just keep it in mind. So, if in a welding operation current is more, their flow rate will be more. Flow rate means flow of this gas per unit time. What I am telling, understand, that will be more. If the current is lesser size, then flow is less. Like in case of microplasma, you can get a flow rate which is varying from 0.1 liter per minute. For a keyhole mode, there can be a flow rate which is 10 liter per minute. That means 10 liter of gas will pass through this nozzle per minute. In case of plasma arc welding process, keyhole stopping is a very critical phenomena, you can say, because in keyhole stopping phenomena, they are generally very high current, we have to drastically reduce to a low current, and that time should be very less. Within a second we have to reduce from high current to low current, and that to convert the keyhole to normal mode, conduction mode types of, or stopping the keyhole. For that reason, there if the flow of this gas will not be proper, then what happen, there is a chance of formation of defect. That is why closing of keyhole is a very important phenomena in case of plasma arc welding process. That is why I will show you in next slide, there is a continuous requirement of monitoring of this flow rate. What I am telling, understand. During a starting of a keyhole, there will be one type of flow rate, during welding type another types of flow rate, and at the closing time also there should be another types of flow rate. That things you should keep it in mind. Once this flow rate will not be properly matched, there is a chances of formation of oxide, and there is a chances of formation of defect. That is why here is a important term used in plasma arc welding process, that is called current and gas decay control. That things here I have just showing. This axis represent plasma gas flow rate, and this axis also represent the current. Here this is the current curve and this is the gas flow rate curve. Here you see the starting of the arc, current is lower side. So, at that time this flow rate also is lower. Once this current is gradually increasing during the starting of keyhole, this flow rate also should gradually increase. What I am telling, understand? And during welding time, as the flow rate current is remain almost constant, at that time gas flow rate also should be constant, you can see here. But at the closing time, suddenly you have to drop down this high current to a very low current. What I am telling, understand? So, at that times your flow rate control also should be slope with that current curve. Once it is not properly controlled, then there is a chances of formation of oxides and defects. Okay, that is why this current and gas decay control is a very important part in case of plasma arc welding process. This you just keep it in mind. Now, what are the composition of this plasma and shielding gas? Always I have told you, generally argon is used as a plasma gas to generate the plasma arc, whereas helium and argon helium mixture generally used for shielding gas. Because helium and argon helium mixture, it is used as a shielding gas because it generally used to increase the thermal conductivity of the gas, and hence it affect the whirlpool heating. What I am telling, understand? This you just keep it in mind, because once we use shielding gas as a helium and argon helium mixture, it can increase the thermal conductivity of gas. Due to this, the heating effect on the whirlpool increase. Okay. Now, here another things you should keep it in mind, helium generally result in a wider types of whirlpool, because once we use helium, as helium has high ionization potential, that is why what happens, once we use helium, there the arc voltage increases, that means arc voltage is more. So, when arc voltage is more, we know that once the voltage is more, then the arc try to spread out, that means wider bead is formed. That is why here I have written helium result in wider whirlpool than argon, it depends on its ionization potential. Now, once we use hydrogen addition to the argon shielding gas, then it tends to promote the slightly narrower whirlpools through the arc constriction. What I am telling, understand? So, hydrogen addition to argon shielding gas tends to promote the slightly narrower whirlpool through the arc constriction. So, these things also you keep it in mind. That means, once we use hydrogen with argon gas, then further construction of the arc is taken place. Now, we will discuss about what are the advantages of this welding process. You see, it has a very high welding speed compared to TIG welding process, 4 times more than TIG welding process. This welding generally possible in different types of thickness of material without the use of filler material. In case of this plasma arc welding process, there we can use a separate filler wire. Separate filler wire, what does it means? Let this is your electrode and this is the workpiece. In between the arc is generated. This electrode generally non-consumable. So, if there is a gap in between these two workpiece, there is used a separate filler wire. What I am telling, understand? This is not connected to any circuit part of the welding machine. What I am telling, it is a separate rod of material which is generally feed to the arc region. Once we feed to the arc region, it is melted and a droplet form and it is generally deposited in this gap. So, this is called filler wire. So, in case of plasma arc welding process, we can do it in autogeneous mode as well as by using filler wire. So, without filler wire and with filler wire also we can do this plasma arc welding process. That is why here I have written butt welding is possible without the use of filler wire, that means without the use of filler wire till 8 millimeter thick plate. Then fusion welding possible is within a range of 0.025 millimeter. there also we can use this plasma arc welding, especially this microplasma arc welding process. That is why this plasma arc welding process widely used in to connect the ball filament with this ball filament support. Generally this microplasma welding technique is used. It is very popular technique. Okay. As this arc is constricted here, that is why here comparatively less heat affected zone, and as the through thickness heating due to keyhole mode, through thickness heating is more or less uniform, that is why due to this uniform heating there is less thermal distortion. These things also you should keep it in mind. Okay. So, in this welding process we can get very low heat affected zone. It is a very advantageous requirement in welding process, and little distortion. This is also very advantageous thing which is required for welding process. Then it has a high arc stability at low arc current, and as this welding process is taken place by using some shielding gases. So, here we can see the arc of this welding process. That is why here I have written here. So, as there is no coverage of this weld pool by using some flux or other things. So, its weld pool as well as this arc is well visible. That is why here I have written in this point, assessment of the weld quality is possible while welding is processed. That means during the welding process itself we can see the weld pool as well as arc progression. That assessment is possible. Another point is its metallurgical quality is in comparison with TIG welding process is better, and it is a flexible welding process. Flexible welding process means this welding process we can use in different form. You can use it in keyhole mode, we can use it in melt-in mode, we can use it in transfer mode, we can use it in non-transfer mode. Disadvantage, yeah, definitely it has some disadvantages also, like here generally this equipment cost is comparatively higher than, you can say very higher than this conventional GTAW welding process. GTAW means gas tungsten arc welding process. Although high arc constriction achieve higher penetration, but it also reduce the tolerance of the process to join gap and misalignment. And here you see the greater complexity of this plasma arc welding torch design and the greater number of parts require more scheduled maintenance. So, here you have seen in this equipment of this plasma arc welding process, there are different types of component, different types of part of this equipment are there. So, to maintenance of this torch as well as maintenance of the equipment require more scheduled maintenance. And another thing which is a very important part, that is called setback of the electrode. Generally here one thing you should keep it in mind in case of this welding process, that means plasma arc welding process. Here you see this electrode generally we keep inside the copper nozzle, that means copper nozzle outlet, that is called setback of this electrode. This electrode we should not come out from this nozzle. In case of TIG welding, this is generally plasma arc welding process. In case of TIG welding process, generally this electrode is coming out from this nozzle. Here you see it is coming out from this nozzle, whereas in this case it is generally this electrode is inside the nozzle. Why it is inside the nozzle? Because here the arc is required to constrict. So, once this arc is passing through this nozzle, then only what happens, this arc constriction is happen. So, this is called setback, this is called setback. What it is called? Setback of electrode. Okay, that which I have written, setback of electrode. This is a very important part of this plasma arc welding process, and to maintain this thing is also very critical types of aspect, you can say. That is I have written the accurate setback of the electrode tip is essential with respect to the nozzle orifice tip, because it is required to maintain consistent result. If this setback things is not proper, then your result will be erroneous. Now, application of this welding process, it has various types of application. Generally plasma arc welding process commonly used in stainless steel material with various range of thickness. It is also can be used for carbon, alloy steel, aluminum, alloy, titanium alloy, copper alloy, nickel alloy, and some specialized types of material that is called zirconium and tantalum, which this zirconium and tantalum is very difficult to weld by other conventional welding process, but by this welding process we can easily weld these things. And this welding process can be used in various thickness within a range of 0.0 to 5 millimeter for microplasma to 12.5 millimeter by single pass only. What I am telling you, at a single pass we can join till this millimeter thickness of plate, like 12 millimeter thickness for aluminum. This welding process generally used in different position. It can be used in manual plasma arc welding process, generally used in all position process. If it is manual plasma arc welding, we can use it in all position. If it is mechanized plasma arc welding process, it is used in flat and horizontal position. And this, what I have already told you, plasma arc welding process can be carried out in autogeneous mode, that is without filler wire also. Without filler, what I have already explained in last slide. Here very important things you should keep it in mind. This is keyhole plasma welding, which is extensively used. Okay, this keyhole plasma arc welding is extensively used for stainless steel pipe and tankage, because the manufacturing of this stainless steel tube from strip was one of the first application of this plasma arc welding process, because this process can reliably produce full penetration without the use of backing. That means this process have a better control along the thickness in case of keyhole mode. So, without backing bar or backing types of support, we can do a very good welding for stainless steel pipe. Now, here I am just showing just some typical components and its joint. Okay. The most commonly joint configuration used with plasma arc welding process is butt joint. Here I have shown you. This joint can be also corner joint or edge joint. Now, here I am just showing some typical example of thickness of 3 different welding process. Here you see for thickness of 3 millimeter thick plate, in case of plasma arc welding process there is not require any root gap. Whereas if we use shielding metal arc welding process or TIG welding process, there is required a root gap of 1 millimeter. That means 3 millimeter thickness of plate. For plasma arc welding process, you see there is no requirement of root gap. If we use thickness for 6 millimeter thick plate, also plasma arc welding process does not require any S preparation. It is a S square but without root gap. But whereas in stick welding or SMAW welding and TIG welding process, it is required around 2 millimeter root opening, around 70 degree included angle, that you can see here. If it is more than 8 millimeter thickness, they are generally required a root face and some beveling operation. But here you see this root face can be around 5 millimeter, whereas here the root face is 1.5 millimeter. So, you can see compared to other welding process how the joint geometry varying in case of plasma arc welding process. In this slide, some of the welding parameter I am showing, experimental welding parameter, like for mild steel, then stainless steel, another example, and titanium. So, from here you can get a fairly good idea what should be the range of current, what should be the range of flow rate of plasma gas, shielding gas. So, you can get a very fair idea. So, here you can see this gas flow rate, that is called plasma gas flow rate, which is varying within a range of what I have already told you, around 10 liter per minute. Whereas in shielding gas can have a flow rate from 10 to 30 liter per minute. Here you see there are 20, 30. So, you can get a very good idea from here depending upon your current voltage range. Another thing also here you can see, if the current is more for mild steel, here you see if the stainless steel current is more, this is 145 and this 2 are stainless steel, here you see, and thickness. So, here for current range here is 145, here is 240, here is gas flow rate is increase. So, higher the current is, higher the gas flow rate. These are the experimental data. So, you can utilize the this concept in actual field. So, this all about this plasma arc welding process. Thank you.